Hello and welcome to see my videos. My name is Matti Ylitalo and today our focus is on heat exchangers. In this picture we see some heat exchanger types. First is a cell and tube, then this plate, spiral, fin tube, and this air-to-air, which is very commonly used in room air conditioning, taking some heat from exhaust air and warming up this incoming air. Then we have this kind of double pipe heat exchangers, plate fins, economizers, and many other types of heat exchangers. Let's start from this cell and tube heat exchanger, and in this video we will learn how we can simulate the behavior of this kind of heat exchanger. On the left here we have a picture showing a typical arrangement in this kind of a heat exchanger. We have a hot fluid coming in, going through these pipes, and we have cold fluid coming into the cell, and we typically have this kind of bubbles which force this cold fluid go up and down. That's a good way to increase the heat transfer on the outer surface of these pipes. In this other picture we have a cell and tube heat exchanger in which we have two tube passes. The hot fluid is coming in, going through these pipes and turning back. The benefit of this kind of arrangement is that when we double the tube length, we double the surface area for heat transfer. That's the big benefit. But the disadvantage of this system is that we need these pipe bends. For this kind of heat exchanger we can calculate the heat transfer rate from this hot fluid. When we know this mass flow of hot fluid and its specific heat capacity and temperature difference between inlet and outlet, we can calculate heat transfer, and if we have very good insulation around this heat exchanger, so no heat is escaping to environment, it means that this heat transfer from hot fluid is increasing the temperature of cold fluid. And if we know the mass flow of this cold fluid and the temperature at cold fluid inlet, we can calculate the outlet temperature of this cold fluid. When we calculate this kind of heat exchangers, we typically use so-called log mean temperature difference method. Then this heat transfer rate is overall heat transfer coefficient times the surface area times this log mean temperature difference. And here we see an example how we calculate this log mean temperature difference for counterflow case, like shown in this picture on the right. The effectiveness of a heat exchanger is a function of heat transfer rate divided by maximum heat transfer rate. And here this maximum heat transfer rate is so-called capacity flow times this temperature difference at inlets. And this capacity flow for hot flow is hot flow mass flow times this specific heat, and capacity flow for cold flow is cold flow mass flow times this specific heat. And in this function we use this minimum of these two values. If you have a given value for this efficiency, You can use it to calculate the outlet temperatures. And here are functions from which you can calculate this outlet temperature for your cold flow and for your hot flow. What will change if we have a multi-pass system? In this picture on the right we see a simple example. Here we have the cold fluid coming into the cell, going up and down and out from here, and the hot fluid is coming in, going into the pipes, turning back in these pipe vents and going out from here. So in this case this system is not more fully counterflowed anymore. If you want to use this log mean temperature difference method to calculate heat transfer in this kind of multi-pass system, you need to add a correction factor to take into account that your flow is no more fully counterflowed. These correction factors depends on your cell pass number, tube pass number, your capacity ratio and so on. You can find these correction factors from open literature. Here is a link to one very good publication from which you can find correction factors for different cases. If we want to use this log mean temperature difference method to calculate heat transfer, we need this overall heat transfer coefficient. And here is a function from which we can calculate this overall heat transfer coefficient. It's having this pipe inside the convective heat transfer coefficient, pipe outside convective heat transfer coefficient, and conduction through wall material. And if we have fouling deposition formation, then we can add this fouling resistance. And if we have water at cell site and water inside pipes, then this typical overall heat transfer coefficients are at level 500 up to 1000 watts per square meter kelvins. Here are two links to my videos in which I have shown how to calculate these heat transfer coefficients in pipe applications. This cell-side heat transfer calculation can be a challenging task. You need to know your baffle spacing, your tube pitches, and your bundle backing, and so on. I added here a couple of methods how you can calculate this heat transfer coefficient. This first one is based on idea that we calculate an open area for flow, and then this Reynolds number, and using that we calculate this Nusselt number from which we get this heat transfer coefficient. In this second method, the idea is that we use this ideal case heat transfer coefficient and divide this cell volume to smaller volumes and use correction factors for baffles and tube bundles. Here are those details for that method, but my idea is that you should think also if CFD calculation would help to get this heat transfer coefficient for cell side. Here are the results of a test case. I asked the Python code from ChatGPT, and by using that code I calculated a case in which my pipe length was 5 meters and I was using 6 passes, so the total length of the pipe was 30 meters. And here we see that this cold flow was at inlet 35 degrees C, and it was increasing to almost 90 degrees C. And at the same time the hot flow was cooling down from 120 to around 90 degrees C. Here we see the detailed results. It's calculating also this LMTD value. When we design this kind of a heat exchanger, we have a big question which fluid we should put inside those tubes. In our example, we had hot water coming in and going through those pipes, and our cold water was coming into the cell side and warming up there. But can this be vice versa? I asked ChatGPT which fluid we should put inside those tubes, and it raised up this question of heat transfer coefficient. It was saying that the tube side and cell side heat transfer coefficients are not equal. Typically, inside tubes we have higher velocity, which means that we have higher heat transfer coefficient. And at cell side we have much lower velocities, which means that this heat transfer coefficient there is much lower. Some kind of a rule of thumb for industry is that we should put always oil inside tubes, also viscous fluids inside tubes, and if we have a dirty falling fluid, we should put that also inside tube. But we need to think about, can we use multi-pass system at all, or should we have only straight pipes which are much easier to clean? If another fluid is having high pressure, we should put that inside tubes. Then we avoid from situation that our cell needs to be a pressure vessel. Because this cell side heat transfer calculation is quite challenging task, my recommendation is that if you don't have a good reference, you should use CFD calculation to optimize your cell side flow behavior. Optimize these baffles and maybe adding some splitter plates near inlet to guarantee even flow through this cell side. Okay, that was all this time. Thank you for watching and see you. Bye bye.